did before coming to TDX. So this is just a small introduction about some general facts about me. I like playing games, board games, video games, and I really like going to haunted mazes during Halloween, and I like watching scary movies throughout the year. And currently, I really like boba tea, and I really like Shiba Inus. So hopefully one day I can own one when I get a house. I speak English and Vietnamese and a little bit of ASL that I taught myself when I was in grad school. And I have some hidden talents, so I have a really good sense of smell, and I can remember things from a really long time ago. So I tend not to forget things once I remember them. Um, and I went to University of California in Berkeley to get my BS in chemistry. And afterwards, I pursued my PhD in both Ohio State, and then I went to UCR to finish up to get a degree in bioanalytical chemistry. And so at UCR, this is where I did my PhD. And as you can see, I never missed a chance to get a photograph with the mascot, Scotty Highlander. And it's at UCR where I learned a lot about designing experiments. And it's here where I also learned how to build an isothermal amplification system, which is very similar to PCR, except there's no thermal cycling involved. It's one singular temperature. And how to tackle the background issues that arise from this technique, because it's notorious for bringing out background signals when there's no target, and it's very mysterious why that happens. I also primarily wanted to look at biomarkers that are in serum. So I looked at circulating microRNA and exosomes, and I also utilized nanomaterials as a tool to help improve the isothermal systems that I looked at. So one particular nanomaterial that I looked at are called cobalt nanoflakes. These are hexagonal in morphology, as you can see in this TEM image right here. They have a positive surface charge, so that means that they can bind to single-stranded nucleic acids very well using the negative backbone. And as I mentioned before, I liked looking at microRNA. MicroRNA, just to clarify, is a short nucleic acid. It's only 18 to 25 nucleotides in length. And we're interested in this because of the abnormal levels that are expressed during disease. So a lot of people look at microRNA in cancer. It's a very popular biomarker in cancer and as other diseases as well, such as diabetes. But the abnormal expression levels are what make this a very popular biomarker from many labs, and that's why we look at them. They're usually protected and encased in exosomes and microvesicles, which enhances their ability to stay stable in circulation, and it wards off nucleases that might attack them. So using these nanoflakes, I use these to enrich the microRNA that's in serum and then extract it into a cleaner buffer matrix. And this is how we used isothermal amplification to detect the microRNA that's on the nanoflake itself. So the technique that I use is called XPAR, and that's short for exponential amplification reaction. So on the nanoflake, on a single nanoflake, if you zoom in, what happens in this technique is the target hybridizes to a template that we added. And when you added a thermophilic polymerase that operates at a high temperature, it will extend the target from 5' to 3'. And in doing so, there's also recognition sequence that's recognized by a thermophilic nickase. So this nickase inserts a nick into the double-stranded species, and this allows the thermophilic polymerase to come in again and peel off the strand where the nick is introduced. And you could repeat this for many, many cycles. And this produces a lot of amplicons. So this amplicon can be stained with cyber gold and detected by fluorescence. So as you can see here, you could have a standard curve ranging from picomolar down to attomolar. And it's also over 6 orders of magnitude. You can get very good a linear fit from that. The sensitivity tends to be around the attomolar range, which is what you would aim for if you want to look at microRNA in serum, because it's a very low concentration. However, you try to do it in serum, the sensitivity becomes higher. It goes from attomolar to femtomolar just because there's a lot of interferences that are present in serum. As you can see, it's so the standard curve becomes a lot more noisy, and that's where a lot of improvements that can be made towards this type of system. However, we still embarked on looking at exosomal microRNA and non-exosomal microRNA. And we can use an immunobead that's decorated with different antibodies that recognize exosomal biomarkers such as CD9, CD63, and CD81. And then by using these immunobeads that are magnetic, you can precipitate out the exosomal fractions and the non-exosomal fractions. These two fractions can then be destroyed using either heat or lysine buffers such as REPA. And using XBAR, we got 2 hits, one from microRNA 155 and one from microRNA 375. We didn't get anything for the other microRNAs that are screened here, and usually these are microRNAs that you would see upregulated during from somebody who has breast cancer. So since this is healthy serum, this is expected. But at an endogenous level, we did pick up some levels of 155 and 375. So after grad school, I did a postdoc at CrossLife Technologies, and this is located in Carlsbad. It's a block away from the Thermo Fisher in Carlsbad, so it's very close by. And that's how I became more aware of Thermo Fisher other than using all the products that we have. But it was during the pandemic, and so you can see it was very, very empty and forlorn. But it was here where I picked up other isothermal techniques such as LAMP, RPA, and HRCA. And it was also here where I learned about using crosslinkers, incorporating them into isothermal technology. So an example of this would be if you have a probe with an NH2 on one end. You could convert it into an electrophilic probe using a crosslinker. And if you have two probes, an electrophilic probe and a nucleophilic probe, you can join them together by bringing them into proximity using a target. So the target will help join the two based on SN2 reaction. And this produces a new target that can serve as a primer for your exponential amplification reaction. So this is the purpose of doing this is just to help bypass reverse transcription so that you could streamline the process more. And it also helps add another layer of specificity to your reaction. And so with a new probe like this, you could do XBAR again and add an endonuclease such as endo4. And this recognizes A basic sites and cuts them very efficiently when it's in a double-stranded substrate. And so with this, you produce an OH at 3' end, and you could go and use a polymerase to extend it. I also used a very similar strategy in a technique called rolling circle amplification. And in this technique, the nucleophile and the electrophile are on the same strand. And you could bring them together using your target. And when they're close enough together, they undergo an SN2 reaction, and you produce a ligated padlock probe. So this probe right here can you'll produce a double-stranded substrate if you use 529 DNA polymerase and a primer. And so this double-stranded DNA padlock will keep, since it's circular, it will keep going on continuously until it runs out of reagents such as DNTPs. So you'll produce a very long strand, and this can be repeated for many, many rounds. An extension of this can include adding RCA primers to it. So this becomes hyperbranched. So these primers recognize the same sequences on this very ever-growing strand. And the polymerase will indiscriminately just keep extending from 5' to 3'. And so you'll produce very, very long amplicons from this HRCA reaction. And these amplicons can be detected by fluorescence as well, using a cyber gold stain or any sort of fluorescent stain in a real-time instrument. And one thing I wanted to point out is that this technique is an exponential growth instead of the linear growth that you would get from a traditional RCA reaction. And it also produces a very clean background right here. So it's a very promising technique compared to other isothermal techniques. And this is a gel here to show you during the ligation, the probe has an impeded migration in the gel compared to the linear form, and that's why it's all the way up here. So after my postdoc, I wanted to continue to look at other opportunities, and this is where it brought me to TDX. And this picture was taken last year when most people were still working from home, so it was very empty. But you know, life goes on, and one of the main projects that I was working on here, that actually I'm currently working on here, is developing a kit to look at IP10 in urine. And the reason why we care about IP10 is that it's upregulated in a lot of maladies. So it's in viral infections and also in immunological conditions. But the main thing that we're concerned about is from kidney rejection. And so this is a way to, it's a biomarker that's used to monitor whether a transplant patient can undergo rejection. So this is a very critical biomarker. There are different methods out in the market right now that look at IP10 and allow you to look at them with good sensitivity. But the main thing that I want to point out is that in our method, we are using Luminex to perform this, and it's the only one here that is currently being built around looking at it in urine. The other ones use plasma and serum or some sort of supernatant from a cell. And it's the only one that's being clinically validated at the moment. So we have collaborators from Duke, Basel, Australia, and in Canada who are helping us to validate this kit. So how this kit works is to detect IP10, we pair a special capture bead from a Luminex bead, and this can it binds to IP10 because it has antibodies on there that recognize it specifically in solution. And those are represented by this capture bead right here, and the red balls are the IP10 in solution. And then afterwards, we wash it one time. And after the wash, we add in a biotinylated detection antibody. So this detection antibody is a secondary antibody that binds to IP10, and it is biotinylated, which is represented by this Pac-Man shape at the FC region. And so after we add that and form a secondary complex, we wash it again, and we add in SAP. So SAP is short for streptavidin phycoethrin. So since the secondary detection antibody is biotinylated, it will pick up a streptavidin phycoethrin molecule. This occurs within at least 30 minutes. And afterwards, we wash off the excess SAP, and then we could resuspend this solution and acquire the data on Luminex. So as you can see, this whole assay takes about 3 to 3.5 hours. And as a result, we want to be able to improve this assay in several aspects, right? So in terms of SOP improvement, we can reduce the time down to less than 3 hours. And we want to be able to also sharpen the procedure so that it's more streamlined and reduce variation from user to user. So before I dive into a little bit more about that, I wanted to clarify how to calculate percent recovery and introduce this concept. So let's say you have a standard of IP10 ranging from 3.125 to 800, and you get the raw MFI output from Luminex, as shown in this table. If you use a 4PL fitting software such as MyAssays, this is the software that we use and it's free online, you could produce a model to calculate or predict the IP10 concentration based on the fluorescence. So this gives you both a calculated IP10 and a theoretical IP10 concentration. So we already know how much IP10 we're expected to have versus what is calculated. So if you take the amount that's calculated divided by the theoretical, multiply by 100, you'll get your percent recovery. So this is a reflection of how close a backfit is to the actual concentration. So ideally, you'd want a percent recovery of 100 every single time. So right now, in the current SOP, we have 3 wash steps, and each of them can add up to at least 45 minutes. And the data that you see at the very bottom right here is what the MFI output would look like at each IP10 concentration and the associated percent recovery. And as you can see at the very high end of IP10, the percent recovery is gargantuan. And one thing that we can do is to improve this SOP is to shorten the time. So if we eliminate the first 2 wash steps and consolidate them all into one, you could see at the bottom right is what the data would look like. And this not only improves your percent recoveries, it tightens the standard deviations as well. So the variation from run to run is reduced. And also, you could see here on the y-axis, the log scale is another order of magnitude higher than if you did all the wash steps. So by eliminating some of the wash steps, you not only shorten the time, you reduce the variation, but you also get a much more robust readout from the Luminex. And so right now, one of the limitations of this technique is that it only works really well in the FM3D. But with a robust reading like this, you may be able to look at IP10 detection on the LS100 as well. And that would be a very welcome change because right now it only works on one instrument. So from this, you could safely reduce the assay time by skipping some of the wash steps. These wash steps collectively may destroy the sandwich complex that's formed on the bead, and that's the working theory for why the signal is enhanced so much when you forgo some of these wash steps, because it helps keep the complex intact. And the user-to-user variation, you could decrease that by not by streamlining the process and not having so many wash steps in between. Another specific goal of this current project right now is to replace the 2 detection and capture antibodies that are in our current kit. These are from a vendor, and we want to be able to have an in-house replacement so that we have more control over our kit components. So right now we have 2 systems right now for the capture and detection antibodies. The one that's currently in the kit is from a vendor called BD Biosciences, and it's a monoclonal mouse antibody. And the one that we want to replace it with, we're looking into a vendor and working with RevMap, and they specialize in monoclonal rabbit antibodies. So to just to review how this process is performed in order to study this, you first have a capture bead and it binds to IP10 and it extracts it from the solution. And afterwards, you add the detection antibody. In this case, we currently use BD. However, we want to replace the detection antibody with RevMap. And so we add a PE conjugated IgG antibody to label that detection antibody so that we can get an MFI readout on the Luminex. And this slide right here shows, it's a very busy slide, but what it shows here is that we are looking at RevMap, a clone of, we're looking at RevMap 120. And so within this 120 family, there are 12 clones. Several of them show a positive output, and then 3 of them are negative. But the bottom line is that of these, several of these subclones respond in a dose-wise manner to IP10. So we know that the binding to IP10 is real. We also can see that we want to be able to have a capture replacement too. And so you can also see here that by using RevMap 120 as a capture now instead of a detection, and if you titrate the detection antibody, it also responds in a dose-wise manner. And so the binding to IP10 here when RevMap is the capture antibody is also real. So RevMap is a very promising antibody that can fulfill both the capture and detection role. However, right now it's still very early, so we want to be able to continue working with RevMap and polish the antibodies that they are providing for us, so that it would be more sensitive and be more specific. And the SOP improvement is an ongoing process. I showed you a preview today of what I've been working on in terms of improving the SOP. But this is something that that is ongoing, and it can always be continuously improved. And also in the near future, I am working to use BLI and SPR to help screen these RevMap antibodies, and also to map the IP10 epitope regions where these antibodies could bind to. So in closing, I'd like to thank these people on the slide, Dr. Dave Lowe and Dr. Ray Pei, for letting me join the team and to work on this project. And Dr. Julie Nguyen, who is currently guiding me on the IP10 assay project. And also to my new team, who they just arrived, Dr. Adak Karamafruz and Audrey Cardoso. It's great to have them on board with us. And without them, I wouldn't have time to be working on this urinassay project. There's also people who used to be in our group, Sylvia Kuhn. She established a lot of the current SOPs that are in place at the moment. Jason Wang, he left us to go to another company, but before he left, he provided a lot of technical training for me. And Tao Ding, she was my ambassador when I first came and helped me get settled at TDX and taught me a lot of the ins and outs. And also the people at the TIC, Dr. Jarha Lee and Dr. Remy Shi, they both provided input and peer review data on what we have so far, and also our clinical collaborators from Duke, Australia, Basel, and Canada. And also to you guys, the audience, thank you for listening. And I'd be glad to entertain any questions that you may have.
Thank you, Michael.
Thank you, Michael.
Yeah.
For the isothermal amplification, I was wondering how do you achieve the primer specificity to the target gene or the microRNA in this case? Because there is no denaturation step in reaction.
Yeah.
Right.
Yeah. So when I was working on it back then, the only control we had over specificity was the temperature, the high temperature. So the idea is that the non-specific sequences wouldn't bind so well at 55 degrees. And that's the only control we had. But if I were to go back, I would envision the best way to add more specificity to it is to have multiple amplification cycles incorporated together, so that only the ones that bind best come out on top. But no, the only way we controlled it back then was through temperature, and that's why, yeah, that's why it is very prone to false positives, and that's one limitation of the assay back then.
Okay, that's interesting.
Yeah.
I have very technical questions. I'm just wondering how many different capture beads did you test? And the other question is, did you also test the different ratios of beads versus IP10 antibodies for your condition to optimize your condition? Would you elaborate those process for me?
So we only tested. Well, when I came in, there was already an SOP established that utilized bead region 23. But so I never deviated from that because I wanted to keep it consistent. But certainly we could look at other bead regions as well, because theoretically they should all be, you know, not read the same way on the Luminex, but they all should perform the same way. And I'm sorry, what was the second question again?
Question was about the ratios of beads versus IP10 antibodies.
Yeah. So right now we use for every test we use 1,500 beads, and that's we other than that we never at least I never tested different ranges of the beads. I did look at them briefly below 1,500, and it didn't really make too much of a difference. But we do need a high bead count in order to incorporate the higher end of IP10. Otherwise, it wouldn't be the solution would be the analyte would saturate the solution, and you wouldn't be able to capture everything.
Michael, I want to help to answer a little bit more this question before you came, and we had Sylvia already intensively study the beads antibody ratio and screen many pairs of antibody, more than 10, and we came out the best one, and that's what passed to Michael. And he's continued to improve and also making internal in-house antibody.
Thank you. So I have additional question about the beads. I think the different beads will have a different sensitivity or different character. So how do we screen beads for optimization of our conditions? So based on your long-term experience on this, would you advise on this, how we decide which beads will be the best?
It depends on your purpose of what you're going to conjugate to. We have a different beads for antibody conjugation versus, or antigen conjugation versus DNA, the probe conjugation. And same kind of beads should perform across the region pretty consistently. If you don't see the consistency, there could be something wrong with handling beads. So if you need more detail, I don't want to waste everybody's time. You can always reach out to us that we can help you a little bit more.
Thank you.
Sure.
Thank you, Ray.
Okay, any other questions from the team?
Can I ask one?
Sure.
Michael, going back to the very beginning of your presentation for precipitating the microRNAs using cobalt nanoflakes, I thought that was pretty interesting. So with all the nanoparticles to research, whether it be titanium or copper, what was it about cobalt that made it outstanding for nanoparticles for precipitating your desired targets?
Yeah, so there are people who do use gold nanoparticles and graphene oxide. If you ever peek at the literature, those are very popular substrates that people use. But it's the nanoflakes. What made them more outstanding was one, they preferentially bound single-stranded nucleic acids, which is usually the nature of microRNA. So that was one attractive feature. The other was just from an empirical standpoint, we did test gold nanoparticles and graphene oxide in comparison with cobalt nanoflakes, and those two just didn't enhance the signal as much as nanoflakes did, and I think a lot of it had to also do with the fact that it didn't. I think it had a very poor extraction efficiency as well. So that's why we use cobalt nanoflakes because of their extraction power and their ability to enhance the positive signal when we were using it in XPAR.
Okay, so you would first was this also doing the RIPA buffer to remove them from the exosomes first, and then you added the cobalt nanoflakes, or did the nanoflakes extract the RNA from the actual exosomes?
We destroyed we first extracted exosomes using an immunobead, and after that we brought it into a clean buffer system, and that's where we used either heat or a RIPA buffer to release the contents of the exosomes and then extract it using the cobalt nanoflakes.
Okay, and then it was able to maintain the integrity of the RNA after they left the exosomes. Like, do you have to worry about degradation at all still?
You do, because well, not as much as you would if you didn't have the flakes there. The flakes sort of provide a steric hindrance effect, so that sort of wards away nucleases that usually would come in contact and degrade the microRNA. But I would say thermal degradation would probably be an issue, so that's why you would want to usually keep it chilled on ice.
Okay. Yeah, very cool. Thank you, Michael.
Yeah, no problem.
Great presentation. Actually, I have also a couple of questions. First, about exosomes, because there are plenty of circulating extracellular nucleic acids in bloodstream and other body fluids. So there's microRNA, mRNA, DNA, etc. And some of them are encapsulated in exosomes. Some of them are bound to proteins, such as AGA2. So certain microRNAs, they're bound to proteins and other entities. So in your experience, kind of what is the distribution of microRNAs, and maybe you can speak about mRNAs and cell-free DNA. So kind of percentage-wise, like what fractions in exosomes, what fractions protein-bound, what is part of other complexes and entities? Just because there were so many discussions in the literature, so I have my personal opinion. So I've heard on exosomes, but so it's a very, very fluid situation. So many groups, they have totally different opinions of that.
Yeah, I personally don't know the percent distribution of all the different RNAs specifically, but I do know that one way the nanoflakes help, I guess, bend the RNAs, because it can also sort of discriminate by size. When we looked at the nanoflakes, they do tend to bind shorter strands more than the longer strands. So mRNA could usually is longer than microRNA, and so that's one way we sort of differentiated the different species of RNA that's in circulation. I don't know if that answered your question exactly.
Yeah, and the second question about just about your selection of the approaches. So you used rolling circle amplification out of many other options. So why exactly you selected that? So it's a good approach, you use it as well, but there are just many alternatives.
I'm sorry, can you repeat that question, please?
Why you selected rolling circle amplification so as your strategy for amplification detection of targets, because there are so many other options, right?
Yeah, so for rolling circle, it was more of just like a personal project that I started just because there's, like you said, there's a lot of different options out there. Some work better than others, and I was really just exploring what was compatible with the targets that we were trying to detect. Sometimes when you use LAMP, it's notorious for having a lot of different primers, and it's very prone to background amplification. So when we kept trying LAMP over and over, it didn't work, and so you look at other things that might might work better. And so I tried my own XPAR reaction, and that worked to a degree, but there was still background. And so that's why I turned to rolling circle, just to see, you know, if that was a viable option compared to what we've tested so far.
Yeah, very cool projects. Thank you.
Yeah, you're welcome.
Great. Any other question for Michael? Well, I guess that concludes this morning's Bagel Brag. I know it's a rainy day, Monday, but happy Monday for everyone. And thank you, Michael, for your talk. And looking forward to your further development of your project.
Thank you.
Monday, guys.
All right, everyone. Have a nice week.